Hi, I am Ethan Parker. Welcome to Lecture 6 in Tech Skill Hub's Beginner Machine Learning course. Last lecture we dove headfirst into regression supervised learning and oh boy are you lucky. Because today we will do the same with supervised learning classification. Classification is a fundamental concept in machine learning that allows us to categorize data into predefined classes. By the end of this lecture, you will understand what classification is, how logistic regression works as a classification algorithm, and the key evaluation metrics used to assess the performance of classification models. What is classification? Classification is a type of supervised learning where the goal is to predict the categorical label of new observations based on past observations. In supervised learning, we have a data set that consists of input features and corresponding output labels. The model learns from this labeled data to make predictions on unseen data. How about an example of classification? Let's consider email spam detection. You might recall this from Lecture 1. In this scenario, we have a data set of emails, each labelled as either spam or not spam. The features could include the presence of certain keywords, the length of the email, or the sender's address. The classification model learns from this data to identify whether a new email is spam or not based on its features. So let's talk types. Classification problems can be broadly categorized into two types. First, there is binary classification. Binary classification is a machine learning algorithm that categorizes data into one of two classes, such as yes or no. It's used to solve problems with two possible outcomes. How does it work? You take data and feed it in, the training data, and the training data is labeled as true or false, positive or negative, or spam or not spam. Then future previously unseen data uses the algorithm to predict whether the input data belongs to one class or the other. Examples of this are our fancy previously visited spam detection. Or maybe customer churn, where you predict if a customer will stop doing business with a company. Or perhaps image classification. Is it a cat or a dog? And how about mobile device authentication, which can determine is a facial recognition legitimate or illegitimate, yes or no, good or bad, angel or devil. We also have multi-class classification. Shocker! This involves more than two classes. For instance, classifying handwritten digits from 0 to 9 based on pixel values. Or is the image a cat, a dog, a shark, an elephant, etc.? Maybe based on keywords, my fancy AI system can determine if an article is about sports, politics, the economy, or surfing. Oh, surfing is a sport. Well, you get my drift, right? So what is the classification process? The classification process typically involves the following steps. Data collection, where we gather a pre-labeled data set. Data pre-processing, where we clean that bad boy data set and get it ready for its big analysis. Model selection, where we get to decide which algorithm will do the best job. Training, where we pit our cool algorithm against the pre-labeled data. Next, evaluation, where we assess how our new amazing model did, using our deeply mathematical evaluation metrics. And finally, prediction, which is where we use this all-powerful new tool to classify new data. Dog, cat, or chimpanzee, right? Now that we have a basic understanding of classification, let's explore one of the most commonly used classification algorithms. This would be logistic regression. So, what is logistic regression? Logistic regression is a statistical method used for binary classification. Despite its name, it is used for classification tasks rather than regression tasks. The key idea behind logistic regression is to model the probability that a given input belongs to a particular class. It is a predictor. And at the heart of logistic regression is the logistic function. Say with me. Logistic function. You are smarter already just saying that. The logistic function is also known as the sigmoid function. Yeah, not nearly as cool, sigmoid. Nope. The logistic function has an S shape. which allows it to model the probability of binary outcomes. The logistic function takes any real-valued number and maps it to a value between 0 and 1. The probability indicates how likely it is that an input belongs to one of two categories. Here is the formula for the logistic function, where z is a linear combination of the input features. This function allows us to interpret the output as a probability. So how does logistic regression work? Magic, of course. Kidding. Here we go, how it works. First, we have the probability modelling. In logistic regression, we model the probability that the output y belongs to class 1, like spam, given the input features x, where w is the weight vector. B is the bias and /sigma is the logistic function. Next, we have the decision boundary. The model makes predictions by applying a threshold to the predicted probability. If the probability is greater than 0.5, we classify the observation as class 1. Otherwise, we classify it as class 0. In third grade math, we called that rounding, but whatever. So then we have training the model. The model is trained using a method called maximum likelihood estimation. This finds the best fitting parameters w and b that maximize the likelihood of the observed data. Simple, right? Now here are the advantages of logistic regression and why it might be an option sometimes. Simplicity. It's just so simple. Logistic regression is easy to implement and interpret. Efficiency. It is computationally efficient and works well for linearly separable data. Those are fancy words, eh? What it means is the algorithm or model to perform calculations with minimal resource usage in the output. Well, that is a dataset where you can clearly separate different classes of data points using a straight line. It has a probabilistic output. In non-crazy man terms, how often does the same set of data produce the same results in our engine? It provides probabilities for class membership, which can be useful in decision making. So what are the limitations of logistic regression? Well, we just talked about it being linear. Logistic regression assumes a linear relationship between the input features and the log odds of the outcome. It may not perform well on complex datasets with non-linear relationships. Last lecture we talked about marketing expenditure and sales not always being linear. And how about in biology? Most organisms exhibit a non-linear growth pattern, starting with slow growth in early stages, then experiencing rapid growth during the exponential phase, and finally reaching a plateau as they mature. Also, let's talk about binary classification. While it can be extended to multi-class problems using techniques like 1v-all, logistic regression is inherently a binary classifier. Yes, no, good, bad, spam, no spam. That, my friends, is an overview of logistic regression. Once we have trained our classification model, it is crucial to evaluate its performance. There are several key evaluation metrics we can use to assess how well our model is doing. First, we have the accuracy metric. This is the most straightforward evaluation metric. It is defined as the ratio of correctly predicted instances to the total instances in the dataset. While accuracy is useful, it can be misleading, especially in imbalanced datasets where one class significantly outnumbers the other. Second, precision. Precision is a measure of the accuracy of the positive predictions. It is defined as the ratio of true positive predictions to the total predicted positives. High precision indicates that when the model predicts a positive class, it is often correct. You may have your head spinning trying to understand how accuracy and precision are actually different. Precision measures how near the calculated results are to one another, whereas accuracy deals with how close they are to the actual value of the measurement. Imagine you're trying to identify cats in a set of images using a machine learning model. Accuracy measures how often the model correctly identifies whether an image is a cat or not, overall. While precision focuses on how many of the images the model labels as cats are actually cats, meaning it prioritizes the quality of positive predictions rather than just the overall correct rate. Clear as mud. Third, we have recall. Recall, also known as sensitivity or true positive rate, measures the model's ability to identify all relevant instances. It is defined as the ratio of true positive predictions to the total actual positives. High recall indicates that the model captures most of the positive instances. There are many other metrics, but let's finish this set with the F1 score. In machine learning, the F1 score is a metric used to evaluate the performance of a classification model, particularly in scenarios with imbalanced classes. By combining precision and recall into a single value, calculated as their harmonic mean, let me explain. To understand the calculation of the F1 score, we first need to look at a confusion matrix. A confusion matrix represents the predictive performance of a model on a dataset. For a binary class dataset, which consists of, suppose, positive and negative classes, a confusion matrix has four essential components. True positives, TP, which is the number of samples correctly predicted as positive. False positives, FP, which is the number of samples wrongly predicted as positive. True negatives, TN, which is the number of samples correctly predicted as negative. False negatives, FN, which is the number of samples wrongly predicted as negative. Using the components of the confusion matrix, we can define the various metrics used for evaluating classifiers: accuracy, precision, recall, and F1 score. The F1 score is defined based on the precision and recall scores, which are mathematically defined as follows. The F1 score is calculated as the harmonic mean of the precision and recall scores as shown below. It ranges from 0 to 100%, and a higher F1 score denotes a better quality classifier. In summary, classification is a vital aspect of supervised learning that allows us to categorize data into predefined classes. Logistic regression is a powerful and widely used algorithm for binary classification, providing probabilistic outputs, outputting the same with the same data. Finally, understanding key evaluation metrics such as accuracy, precision, recall, and the F1 score is essential for assessing the performance of classification models. There are some haughty terms in here today, right? Well, do not be afraid of them, and when you're confused, well, just don't be, after all. Edward R. Murrow said, "Anyone who isn't confused really doesn't understand the situation." Think on that. I appreciate your time, and I will see you next lecture. Cheers and have a blessed day. Please like and subscribe for the sake of Tech Skill Hub and all of the flies that annoyed the heck out of me while I was putting this lecture together and met their fate at the end of my swatter. This is Ethan signing off.